Hey, welcome to The Explainer. Today, we're going to dive into something that powers, well, pretty much everything around us. But here's the crazy part. You can't even see it. We're talking about the current of electricity. Let's get right into it. Just take a look at that, Every single light you see, the phone that's probably in your pocket right now, the screen you're watching this on, it's all made possible by an electric current. Think of it like this invisible river of energy, just constantly flowing through wires and bringing our entire world to life. So that's the big question, right? What even is that flow? I mean, what is literally happening deep inside those tiny wires to make everything work? We flick a switch, and boom, there's light. But how? Well, that's the mystery we're going to unravel today. Okay, first things first. We've got to understand the river itself. So for part one, let's talk about the flow, which, in the world of physics, we call the electric current. So what is it exactly? Well, electric current is basically the rate of flow. It's not just that charge is flowing, but how much charge is zipping past a certain point every single second. Kind of like counting how many cars pass a spot on a highway in 1 minute. And the unit we use to measure this flow is amperes, or you'll usually just hear it called amps. All right, now here's where things get a little weird, thanks to history. Way back in the day, before anyone even knew what an electron was, scientists just guessed. They decided the current flowed from the positive side of a battery to the negative. We call this conventional current. Turns out they were wrong. It's actually the tiny, negatively charged electrons that do the moving, and they go from negative to positive. But, and this is super important, we still use the old school conventional current direction in all our circuit diagrams. So yeah, you gotta remember that one. And of course, since this is physics, there's a formula for it. But don't worry, this one's super straightforward. If you want to know the total amount of charge that's flowed, that's Q, all you do is take the current, I, and multiply it by how long it's been flowing, T. That's it. Total charge equals current times time. Simple, right? But believe me, it's incredibly useful. Okay, so we've got this flow of charge. But wait a minute, charges aren't just going to start moving all by themselves, are they? They need a push. So what's giving them that push? Let's find out in part two. One of the absolute best ways to wrap your head around electricity is to think about water. Seriously. Imagine the wires are pipes and the electric charge flowing through them is water. So what makes water flow through pipes? A pump, right? The pump gives the water the energy to get moving. Well, in a circuit, the battery, that's your pump. It provides all the energy to get that charge flowing. So this big push from the battery has a fancy name, electromotive force, or EMF for short. Don't let the name scare you. All it means is the total energy the battery gives to each little package of charge to get it all the way around the circuit. Think of it as the maximum power boost the pump can give. But what about when that charge actually does something useful, like making a light bulb glow? Well, the energy it spends to get through that bulb is called potential difference, or more commonly, voltage. Let's go back to our water pump. The pump gives the water a big push, right? But if that water has to turn a big water wheel, it's going to lose some of that energy. That energy drop across the water weir, that's the potential difference. It's the energy used up. All right, we've got the flow and we've got the push. But is it always smooth sailing for those little charges? Not exactly. There's usually something getting in the way, an obstacle. Let's zoom way in, right down to the atomic level of the wire. It's not an empty highway. It's more like a crowded hallway packed with vibrating metal atoms. So as our electrons try to zoom through, they're constantly crashing and bumping into everything. It's a bit of a pinball machine in there. And all that bumping and crashing, that opposition to the flow, that's what we call resistance. And we have a way to measure this electrical friction, of course. We use a unit called the ohm. So resistance, which we call R, is really just a ratio. It tells us how much push or voltage you need to get a certain amount of flow or current through something. It makes sense, right? If the obstacle is bigger, you're going to need a bigger push to get the same amount of flow. So let's recap. We have our three big ideas. The flow, that's the current, the push, that's the voltage, and the obstacle, that's the resistance. And here's the beautiful part. In physics, these three things are all connected by one elegant, super powerful rule. And here it is, Ohm's law. It's probably one of the most famous equations in all of physics. V equals I times R. Or, if we put it back in our simple terms, the push equals the flow times the obstacle. Voltage equals current times resistance. When you think about it like that, it's just common sense, isn't it? Okay, enough theory. Let's see this thing in action with a real-world example. So you've got a regular clothes iron. We know the push it's getting from the wall socket is 240 volts, and we measure the flow of current going into it as 8 amps. The question is, how big is the obstacle? What's its resistance? Let's walk through the thought process. Step 1. We need to find R, so we just rearrange Ohm's law. A little bit of algebra gives us R equals V divided by I. Easy. Step 2, we pop in the numbers we know. So R equals 240 volts divided by 8 amps. Step 3, just do the math. 240 divided by 8 gives us 30, so the resistance is 30 ohms. Done. See? Ohm's law makes it easy. So we figured out the iron's resistance is 30 ohms. But why? Why 30? Why not 5 or 500? What is it about that iron that sets its resistance? What makes the obstacle bigger or smaller? Well, it turns out there are 4 main things that affect resistance. First, how long the wire is. The longer the wire, the more stuff the electrons have to crash into, so more resistance. Makes sense. Second, how thick the wire is. A thicker wire is like a bigger pipe. It's easier for everything to flow, so thicker means less resistance. Third, the type of material. Some materials, like copper, are just naturally easy for electrons to move through. Others aren't. And last but not least, temperature. Yeah, temperature is a really interesting one. Remember that crowded hallway filled with vibrating atoms? Well, when you heat up a wire, those atoms start vibrating like crazy. They're jumping all over the place. And that makes it way, way harder for the electrons to squeeze through without a collision. So for metals, hotter means more vibrations, which means more resistance. And as you can see from the graph, it's often a really neat, predictable, straight line relationship. Okay, but just when you think you've got it all figured out, physics throws you a curveball. That perfect, simple V equals I times R rule, yeah, it doesn't apply to everything. Some things just don't play by the rules. We call these little rebels non-ohmic conductors. And the classic example is an old-school filament light bulb. Think about it. When you pass a current through that tiny little wire inside, what happens? It gets super, super hot, right? That's how it glows. And what did we just learn about metals getting hotter? Their resistance goes up. That's exactly why its graph isn't a straight line. As more current flows and it heats up, its own resistance changes. The obstacle actually gets bigger the more you push. So we've talked about resistance getting bigger, but what if you could make it go away? Like, completely? Well, you can. This is where we get into the amazing world of superconductors. When you cool certain materials down to incredibly low temperatures, their resistance suddenly drops to 0. Absolutely nothing. And that means a current can flow through it forever without losing any energy. It lets you do incredible things like make a magnet just float in midair. And that kind of brings us full circle. We started this whole thing by trying to understand the obstacle resistance. We've seen what causes it, what changes it, but now we've also seen that it's possible to make it vanish completely. So that's the final question I want to leave you with. Now that we know what resistance is, what amazing, world-changing things could we build if we could make that obstacle just disappear? That's a fun one to think about. Thanks so much for watching.